Hello everyone and welcome to Introduction to Biostatistics and Epidemiology Part 2. And again, my name is Gabrielle Cahill. So last week we learned about populations and samples, epidemiology and descriptive statistics, or how to describe your data. Now we will begin to describe inferential statistics, or how we go about drawing conclusions about populations from our samples. Our learning objectives for today are to understand basic concepts in probability, to understand the structure of hypothesis testing, to understand what a p-value is and what a confidence interval is, and to understand the types of error and power. And here's the outline for what we'll be learning today. As I mentioned, last lecture we learned about descriptive statistics and discussed measures of association to describe epidemiological data. What we really want to know is, are our study samples truly different? Does exposure have a true effect on outcome? As you can see in this table, the means and standard deviations, or medians and interquartile ranges that you can see here, describe the data, but the p-values listed along the side on the right require us to make inferences about the underlying populations from which the samples are drawn. We will discuss more about this throughout the lecture. To make these conclusions, we need inferential statistics, statistical tests, and a testing framework. So to do inferential statistics, we need to have an understanding of probability because this is the mathematical foundation for statistical inference. To start, we will discuss some terminology. An event is a potential outcome that may occur. It either occurs or does not occur. When probabilities are written in an equation form, the events are written as capital letters. Probability is the likelihood that something will occur, the relative frequency that something should occur, or the proportion of time the event occurs if the same test or process is done multiple times. Probabilities lie between 0 and 1 and can also be described as percentages. For example, a probability of 0.1 would be the same as 10%. The probability of an event is written out as P, the letter of the event in parentheses. There are various laws we can use to calculate how likely an event is to occur, and the law that should be used depends on the characteristics of the event. Mutually exclusive events are events that cannot occur simultaneously. For example, I cannot eat dinner and not eat dinner at the same time. If I'm picking a single card out of a deck of cards, I cannot pick a black card and a red card at the same time. When dealing with mutually exclusive events, we use the law of addition. The chances of either event happening are the chances of one plus the chances of the other. And the equation you would use to describe this is written on the slide here. Both of the examples I gave above are special cases. They are called complements because either one can happen or the other can happen. The only two choices are to either eat dinner or not, or to pick a red or a black card. Therefore, their probability adds to 1 or 100%. Two events are independent if the outcome of one event has no effect on the outcome of the other event. For example, if I flip a coin, the result I get has no bearing on the result of a second coin flip. If I flip a coin and get heads, this has no influence on whether or not I will get heads the next time I flip the coin. As another example, let's say my friend has a baby boy. The chances that they will have a baby girl next is not affected by the fact that they already have a boy. With independent events, we use the law of multiplication. The chances that both happen are the chances of one happening multiplied by the chances that the other happens. And that's also written out mathematically on the slide here. What if I want to know the chances of multiple events occurring, but they're not independent? That is, the chances of the second event happening depend on what happens in the first event. Now, the chance that both occurs is equal to the chance of the first event times the chance of the second event given that the first occurred. This is written out here mathematically on the slide, where B with the line and then A means B given A. Now let's look at some examples. What is the probability that I pick an 8 from a deck of cards? I know that there are 4 8s in a deck of 52 cards, so the probability that I pick an 8 from a deck is 4 out of 52. If I picked a random card from a deck of 52 cards an infinite number of times, the number of times I picked an 8 would approach 4 out of 52, the probability that this would happen. Now another example. I put the card back and pick a new card. What is the chance this card is a red 8? There are 2 red 8s in the deck I could pick. Since I'm only picking one card, these events cannot occur simultaneously. They are mutually exclusive. Therefore, I can use the law of addition. The probability of picking a red 8 is equal to the probability of picking an 8 of hearts plus the probability of picking an 8 of diamonds. 1 over 52 plus 1 over 52 equals 2 over 52. And that's the chances, the probability that I would pick either of those if I picked a single card from the deck. What is the chance of me picking an 8, picking any 8, replacing it, putting it back in the deck, and then picking a red 8? The chances of me picking any 8 are 4 out of 52. The chances of me picking a red 8 are 2 out of 52. These events are independent because as long as I replace the 8 after I pick it, the chance of picking one of the 2 red 8s does not depend on the chance of me picking an 8 the first time. Therefore, I can use the law of multiplication to determine the chances that both will happen. 4 out of 52 times 2 out of 52 equals 8 over 2,704. Or 0.3% of the time, if I pick a card out of the deck, replace it, then pick a new card, the first will be an 8 and the second will be a red 8. What if I didn't put the first 8 back? What is the chance of me picking any 8 and then another 8? Now the chances of me picking an 8 the second time depend on what happens the first time, because if I pick an 8, there are less 8s left to pick. The probability of picking any 8 is still 4 over 52. But if the first card I pulled is an 8, there are only 3 left in the deck and 51 cards left to pick from. So now we have to use the law of conditional probability. Using that law, the chance of picking any 8 and then another 8 is the chances of the first times the chances of the second given that the first occurred. This is equal to 4 over 52 times 3 over 51, or 1 over 221. We will often assume certain things about our samples, like that events that might occur are independent or that things are conditionally independent. So it's important to understand these concepts about probability. Now that we have covered them, we'll go back to talking about statistics. When we talk about doing a study, we typically have a hypothesis or an expectation of what we think will occur. When doing inferential statistics, we come up with a null hypothesis and then do statistical tests to determine whether or not to reject that null hypothesis. So what is the null hypothesis? It is the hypothesis that there is not a difference between certain characteristics of groups, or that a given parameter, for example, the mean, is not different from a certain hypothesized value. An example of this, going back to our height example, could be that there is no difference between the heights of men and women. The alternative hypothesis is that there is a difference between the groups. In our height example, that there is a difference in height between men and women. When we do a statistical test, formulating the null hypothesis is the first step. We would then choose an appropriate statistical test to use and calculate the test statistic that is associated with that test and compare that calculated value using the data from your sample to the known distribution of that test statistic. This allows you to decide whether you have enough evidence to reject that null hypothesis based on your pre-selected level of significance, or whether there is insufficient evidence to reject the null, and you decide that there's no significant difference between your groups, or that the parameter you calculated, for example, a mean or a proportion, does not differ significantly from your hypothesized value. So again, if you reject the null, you would accept your alternative hypothesis. And if you have insufficient evidence to reject the null, you would determine that that alternative hypothesis is not true. As I mentioned, once you've determined your null hypothesis, you can test it. You compute the test statistic using the sample values. And these test statistics have known distributions. So you can compare the value of the test statistic to that distribution to see how likely it would be for samples to result in a test statistic of that magnitude. So on this graph, this is some example of different distributions that you would use for different test statistics. The yellow arrow shows in this region the chance that samples from the same underlying population would result in a test statistic as great or greater in magnitude as the one computed using our observed values is very low. There aren't that many values on this graph that are more extreme. And the green arrow, the chance is relatively high. All of this area has greater magnitude. So we would accept that the samples come from the same underlying population. You may have heard of a p-value before. This is the probability that a result as extreme or more extreme than the one we observed would occur due to random variation if the null hypothesis were true. You then use the testing framework to decide whether or not to reject the null based on how it compares with the pre-selected critical value, called alpha. Oftentimes, alpha is 0.05 or 5%. If p is less than alpha, we reject the null hypothesis and accept the alternative hypothesis. It is likely that the two samples came from two different populations, or that your parameter does vary significantly from the hypothesized value. An example of how we would use a p-value. If p is less than 0.05 when comparing heights of men and women, where our null hypothesis was that there was no difference between the heights of men and heights of women, we would reject the null and conclude that there is a statistically significant difference between the heights of men and the heights of women. Another example of how we would interpret a p-value. Last week, we discussed measures of association and how if there's no association, the cumulative incidence ratio would be expected to be 1. Our null hypothesis would be that the cumulative incidence ratio equals 1, that there was no association between antibiotic use and number of infections over the study period. If, after doing our statistical test, we find that p is less than 0.05, we would reject the null hypothesis and conclude that treatment with antibiotics did have a statistically significant effect on the risk of wound infection. The p-value and the framework of hypothesis testing are very important tools. However, they don't tell us about the direction and magnitude of different groups. For example, we have concluded that men and women have different heights, but which group is taller and by how much? It also doesn't tell us the actual population parameters. We have concluded that there is an association between antibiotic use and infection risk, but what is the magnitude of this effect? Instead, we can use point estimates and confidence intervals to provide this information. Often we use a 95% confidence interval, which has to do with what we choose for alpha, which, as I mentioned, is typically 0.05. And 1 minus 0.05 is 0.95 or 95%. So what really is a confidence interval? A 95% confidence interval means that 95% of the confidence intervals we create will include the true value of the parameter of interest. If we took 20 samples and made 20 point estimates and 20 95% confidence intervals, 19 or 95% would contain the true population parameter. In other words, we are 95% confident that the true population parameter is contained within this interval. Note that this does not mean that there is a 95% probability that the true value is contained within the interval for any given confidence interval. But we can be 95% confident that the true value, for example, the true cumulative incidence ratio in our antibiotic example, is contained within the 95% confidence interval. Here is an image of 20 confidence intervals. The true value is the dotted red line, and every point estimate is shown with a blue dot. This would be the value that we would calculate using the sample. For example, the mean height difference between men and women in our sample, or the cumulative incidence ratio calculated with our study participants who were either given antibiotics or not. Each of these point estimates is slightly different because each of our 20 samples is slightly different, and each of the confidence intervals is also a bit different because of variation in the different samples. 19% of these confidence intervals contain the true value. However, by chance, one does not. This aligns with our expectation that for a 95% confidence interval, 95% of these intervals will contain the true value of interest. There are other confidence intervals you can create, for example, a 90% confidence interval or a 99% confidence interval. And the confidence we have that that interval will contain the true value of interest aligns with that 90% or 99%. The size of a confidence interval also changes with that value. A 90% confidence interval will be smaller than a 99% confidence interval. Now let's discuss types of errors. The alpha that we discussed earlier is that critical value corresponding to the false positive rate. If we pick alpha equals 0.05, this means that we accept that 5% of the time we will reject the null and conclude there is a difference when in fact there is no difference. Beta is the false negative rate, or the rate at which when there is a real difference, but we fail to reject the null hypothesis and conclude that there is no difference, when really there was. At the bottom here, you can see a 2x2 table showing the different possibilities. We can either reject the null hypothesis or not, and the null hypothesis can either be true or not. If we don't reject the null hypothesis when it was true, this is a true negative. There was no difference, and we concluded there was no difference. If we reject the null hypothesis when it was true, we have committed a type 1 error. This is a false positive. We concluded there was a difference when really there wasn't one. This is alpha, which we decide in advance. If we don't reject the null hypothesis when it was false, this is a type 2 error. It's a false negative because we concluded there was no difference when really there was. This rate is described by beta. If we reject the null hypothesis when it was false, this is a true positive. We said there was a difference and there really was. This rate is 1 minus beta and is also called power. Power is the ability of a test to conclude there was a difference when in fact there was a difference. It is directly related to sample size and the magnitude of difference between the groups. The larger the difference, the smaller the sample size needed to ensure we will be able to detect this difference between our groups, or in other words, to power our study. The larger the sample size, the smaller the difference we will be able to detect. If we know or can estimate the difference between groups, we can calculate the needed sample size to ensure our power is sufficient. Usually we choose between 80 to 90%. So now that we know a bit about testing frameworks, p-values, confidence intervals, types of error, and power, we are ready to begin learning about the actual statistical tests we will use within this framework. On the right is an image of many different kinds of statistical tests that you could choose. Which one is the right one? This depends on the type of data you have and the question you want to answer. For example, is your data categorical or continuous? Do you want to compare to a known population value or to another sample? How many samples? You can use this type of flowchart to help guide your choice. Next week, we will learn about some of these different tests, how to calculate the associated test statistics, and practice going through the testing framework in order to draw conclusions about our samples. See you then.